This is an example problem showing you how to calculate the force acting on a charged particle in a line of other charges. To begin with in the calculation, we're going to find magnitude and direction, and then along the way, we're also going to show you some calculator trips to help you do the calculations. Question is to find the net force on the 12 millicoulomb particle. I'll start that with a free body diagram. So I'm just going to put a dot on my page, and the dot represents the 12 millicoulomb charge. Then I'll look at the other charges one at a time. To begin with, I'm going to start with the -4 millicoulomb charge. That's negative. The charge in question is positive. They're oppositely charged, so they would be attracted towards each other. I'm just focusing on the charge in the question, which is the 12 millicoulombs, and it will be attracted towards the -4 millicoulomb charge. So I'll put an arrow going towards the -4 millicoulombs. Then I'll look at the 2 millicoulombs. It's the same charge as the 12, so it would be repelled. So in this case, the 12 would be repelled away from the 2 or moving to the left. Now, if I had more charges, I would just keep adding the arrows, adding them tip to tail, either to the left or to the right as they attracted or repelled. Okay, now you're probably wondering, do I have to draw a free body diagram? And the answer is yes, you have to draw the free body diagram. Don't skip it. It's going to help you to figure out what goes on as the problems get more complex. Next, I got to find the magnitude. And to find the magnitude, what I'm going to do is use Coulomb's law, KQ1, Q2 over R squared for each of the pairs of charges. So the 2 and the 12 and the -4 and the 12. I'll put in my values, 8.99 times 10 to the 9 and 2 times 10 to the -3. So when I'm doing the times 10 to the -3, that came from the fact that there was an M in between the number and the letter C, which is the unit. And so that letter M stands for milli, or times 10 to the -3. And when I'm finding the distance, that's 4 times 10 to the -6. And I know it's times 10 to the -6 because I replaced the Greek letter mu with times 10 to the -6. So that's going to be our micro extension. And then when I do the calculation, I get 1.35 times 10 to the 16 newtons. But you don't want to round it because you're going to use it later. So I need to keep all those decimals. To do that, I'm going to store it in my calculator under the letter A. And then on my paper, I'm actually going to write a little a with a circle around it. It doesn't mean anything mathematically, anything about science. It's just a notation to me that I stored it in A so I can remember that later. That's all that does. Now I'll go and do the calculation for the other charged particle, the -4. After, I show you what the calculator screen looks like. First off, I've got K. So in class, we stored 8.99 times 10 to the 9 into the letter K. So all I need to do when I'm using 8.99 times 10 to the 9 is type the letter K on my calculator. So that's what the K stands for. And then 2 e to the -3 times 12 e to the -3 divided by 4 e to the -6 squared. I'm not using that notation of times, 10, and then a caret symbol. I've got these e's popping up. So those e's are a great shortcut built into the calculator. They do a couple things for you. First off, they use less screen space, so it's easier to see what's going on. Second thing they do is they actually tell the calculator that the 2 and the times 10 to the -3 go together when you use that E command. When you are writing your final answer, though, you need to write it in math. This is basically texting. And in texting and formal writing, we know in formal writing we don't include texting characters. We do formal writing. So if you're going to use that E notation, you can't use it in the answer, only on the calculator. So your calculator looks something like this. To use the EE, you're going to press the second button and then the EE key, which is above the comma on a graphing calculator. It's not just on the graphing calculator, it's on other calculators too. But the graphing calculator is nice because it's color-coded. Next, I'll do the next calculation. And notice that there's no negative sign because I'm finding the magnitude of the force. I don't need to do a plus or minus for the direction. So I'll leave the negative sign off my calculations. And then I get 8.81 times 10 to the 15 newtons, and I'm going to store that in my B location. So here's my notation again, a B with a circle around it. My calculator screen is going to look something like this. K, 4 e to the -3 times 12 e to the -3 divided by 7 e to the -6 squared. Cool little trick here with the calculator, especially a graphing calculator, is you can press second and enter and it'll retype the previous calculation, and then you can use the arrow keys to move around and change numbers to match the new problem. All right, let's keep solving this. Net force. So to find the net force, what we're going to do is say all the forces pointing right minus all the forces pointing left. This is kind of easy because I only have two forces, one points right, one points left. But I'm making everything that's going to the right positive in my equation. Everything going to the left will become negative. So this is basically what I'm doing. I know that the force of negative 4 on 12, that points to the right, so I made it positive, minus the force of 2 on 12, that points left in my free body diagram, so I'm going to make that negative. And it's going to be really easy because I stored them in my calculator to type in all the decimals. Because in my calculator, I'm just going to write b minus a. Easy. So here's what I'm doing when I'm doing the subtraction. And that's going to give me an answer of 4.68 times 10 to the 15 newtons. And it goes to the left. I know it goes to the left because when I put it in the calculator and I got my answer was negative. And remember, about 3 lines up, it said all forces pointing right minus all forces pointing left. So to the right is positive, to the left is negative. So when I got my negative answer, I knew that it also went to the left. Now, if we're looking at the solution steps to show, we're looking for the free body diagram with the labeling of the forces, Coulomb's law to calculate the forces' magnitudes, drop the signs, use the free body diagram to create the summation formula, and then we'll do the math.